Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. Actually, this is the AAS Journal Author Series. And I am super happy to have Avrajit Bandyopadhyay with us today. Hey, Avrajit.
Hi, Frank.
How are you on this October 20th of 2022 as we shoot this?
Yeah, I'm doing good. Thank you. How are you doing?
I am doing awesome, primarily because the weather in Phoenix has changed. So we've gone from summer into our fall weather. So the air is nice and dry now. It's fairly a little cool in the morning, cool being a relative term, and then it warms up. So it's a very pleasant time right now in Phoenix. And Avrajit, where are you located at?
Yeah, I'm currently at Gainesville, Florida, the
Oh,
University of Florida. And even here, it's getting cold.
oh, okay. Gainesville. Yeah, you're about halfway up the state or so. So yeah, very good. Were you impacted at all by Hurricane Ian?
Sorry?
Were you impacted at all by Hurricane Ian?
The Hurricane Ian just missed Gainesville by 100 kilometers, by 100 miles.
Okay. But you still got some rain and...
So we had all the preparations, like packing our house and everything with stuff, but ultimately nothing happened,
Okay.
thankfully.
Well, that's a good thing. So very good. Very good. And what is your position there at Gainesville?
So here I'm working as a postdoctoral research fellow.
Very cool. Very nice. And speaking of postdoctoral research, what kind of research do you like to do, Avrajit?
Yeah, so I mainly work on stars, like the stellar evolutions, the evolution of the galaxy using stars as the integral component,
Cool.
and then the nucleosynthesis channels, and like finding out the oldest stars and the chemistry of the oldest stars and how the elements form, and tracing back to the first stars. That is my primary work.
Nice. Very nice. And that is going to bring us to this very lovely, most awesome APJ article. It's open access, era of open access, people. You can go grab a copy for free, get one. And we have lithium distribution, kinematics, and detailed abundance analysis among very poor metal stars in the galactic halo from the HESP-GOMPA survey. And Avrajit, take us away.
Thanks a lot for the introduction. So this is a work done by us. The team includes me, Shivrani from Indian Institute of Astrophysics, Tim Beers from University of Notre Dame, Sushmita, again from Indian Institute of Astrophysics, Prashant K. Nayak, this is from TIFR Mumbai, and Jeevan Pandey from AAS, Aryabhatta Research Institute at India.
That's a nice shout out.
Yeah, thanks. So this team primarily worked on the study of lithium to prove the kinematics, the abundant study of stars that have lithium. And this study is a part of the bigger survey called the HESP-GOMPA survey. So the HESP-GOMPA survey is Henle-Eshel spectrograph, and the GOMPA is Galactic survey of metal-poor stars.
Okay.
So this survey we do to study stars that are metal-poor. Metal-poor implies stars that are old, to do the abundances and see the distribution and how they chalk out in terms of the galactic chemical evolution.
Yes. Okay.
Yeah. So the goal of a study is to look at the pristine conditions in early universe. And the subject that we work on is called stellar archaeology. It involves digging the history of the cosmos using the oldest stars that are still existing in the Milky Way to this day. And one of the very important elements that we observers can look into the stars is, of course, lithium. So one of the main reasons why lithium is important is because it was formed in the Big Bang. It is one of the very few elements other than hydrogen and helium that are formed in the Big Bang and has got mixed in the interstellar matter in the following epochs and is still found in the outer layers of the star.
Okay.
So if we study lithium, we can get an idea about the mixing of the ISM at the earliest epochs of star formation and the evolution of the stars to the galaxy in the galactic time scale. And another property about lithium is that it's easily destroyed at higher temperatures. So as the star ascends the giant branch after passing the main sequence turnoff, lithium starts depleting. Yes. And so the abundance of lithium goes down in the case of giants. And so it's an element that can be used as a yardstick to study the stellar evolution of the individual stars, the formation epoch of the stars by indicating the mixing of the ISM that it has undergone. Okay. So the other motivations include like study the abundance of lithium in different classes of metal-poor stars. Like these metal-poor stars, for example, are process-enhanced stars. carbon-enhanced metal-poor stars, stars in globular clusters, are formed at primarily the similar epochs, but they show different nucleosynthesis history.
Yes.
So lithium is an element that, so we want to study whether lithium can show some different characteristics for these different stellar systems. So lithium abundance in different classes of metal poor stars, the mixing of lithium, the lithium abundance after mixing in the ISM, lithium abundance of stars in the halo as a function of distance. So
Yes.
here by halo, by the galactic halo, we mean the chemical halo, the halo that is Fe by H less than -1. So
Okay.
metallicity less than -1, which may not be identical to the kinematic halo
Right.
that has a velocity of greater than 180 kilometer per second with respect to the local standard of rest. So these two halo are not exactly identical, but here by halo stars we mean the stars that have halo-like orbits.
Okay. Good. Good.
And we also want to probe the origin of lithium, whether are they formed in the Milky Way, are they accreted from other dwarf galactic systems, and differentiate them using motions of the stars. And we also want to indicate so when lithium was initially studied, they showed a constant abundance called the speed plateau.
Yes.
At abundance of lithium equal to 2.2.
Uh-huh.
So we want to study how this speed plateau varies with the galactocentric distance. Are they different for different classes of stars?
Yes.
Recent studies have come up with a slope of the speed plateau. Do we see the same slope as we go with distance? So these are some primary questions that we want to address in this study.
Cool.
So, yes. So as we come to the target selection, so here in this study, we take stars from the low resolution Marvel's SDSS survey.
Okay.
So we take up some best metal poor targets from the SDSS Marvel survey and re-observe them using HESP, or the Hanley-Eschel spectrograph, on the Himalayan Chandra telescope.
Nice.
So here in this study, we have put up 12 stars, which are primarily metal poor stars with metallicity less than -2 or around metallicity -2. I think this is table 1. This shows the observational details like star names, the coordinates, the exposure times that we have used, the signal to noise ratio that we have achieved, along with the V magnitudes and the radial velocity.
Yes.
So they were observed, as we can see in this log, for 2 or 3 exposures for each star. And then the data analysis was done using like the IRF, PIRF are some of the tools that we use to reduce the data. And then we use turbo spectrum using Kuruk's plane parallel atmospheric models,
right,
one-dimensional LTE. So we use these models using the code turbo spectrum to derive the spectral template, and then we derive the stellar parameters. Now, coming to stellar parameters, the stellar parameters of these stars could be determined by several processes. One is, of course, the photometric usual color temperature, like V minus K.
Yes.
We can get temperature from spectroscopy by other means, like excitation potential of iron 1 lines. We can use broad features like the hydrogen features, like H alpha and H beta features.
Right.
And same for log G, we can use several means like the broader wings, like of the magnesium wings. We can do the Fe1 by Fe2 lines. We can also do it from Gaia. So if you come to figure, I think figure 1.
Figure 1.
Yeah.
Let's take a look at these spectra. There we go.
So here I show on the top, I show the H alpha feature for different temperatures. Like the wings of H alpha are sensitive to small variations in temperature. As you can see, red is the best fit, and blue and black varies by 100 Kelvin.
Okay.
So we take the best fit in H alpha, and then on the bottom, we show the magnesium triplet that is very sensitive again to the variation of log G. So red shows again the best fit in log G, whereas blue and black are deviations from the best fit.
Okay.
So this is one of the methods that I was talking about to determine the stellar parameters. So you include all these methods in table 2 for temperature, and table 3 to show the different estimates for temperature and log G.
Okay, good.
Yeah, and on table 4, we show the adopted stellar parameters. Like so here, like for example, in table 3, we can see the estimations of log G from Gaia parallax. And the equation on the left shows that like the usual technique to get the estimates of log G from Gaia parallax. And on the table 4, we show the adopted final parameters that is consistent with all these methods. And the uncertainties in the stellar parameters are obtained by the like varying temperature by 150 Kelvin and log G of 0.25 dex and re-estimating the parameters.
Okay, good. I'm with you.
Yeah. So now we come to the individual abundances of these stars. So as we can see in if you come down to maybe figure.
Let's go down to figure 2.
Yeah, figure 2.
That's lithium.
Yeah. Yeah. So this figure 2, like this is an example of the synthesis we do to derive the abundances. For example, this is the lithium line at 6707 angstrom. And these are the two stars where red shows the best fit and blue or black are again deviations from the best fit by 0.05 dex.
Okay.
So this is an example of spectral synthesis that we do to determine the individual abundances of each element. Like similarly, in figure 3, we show the synthesis for carbon. Like carbon, we have used the carbon G band, like CH molecular band at 4300 angstrom. Here, right. So again here, so this is the signal to noise of this region isn't great,
right?
But still, we can do a reasonable job in constraining the abundances of CH if we know the other parameters in precisely. So here again, red shows the best determination of carbon abundances, whereas blue and black are deviations from the best fit by 0.5 dex. So this is how we determine the stellar abundances of the different elements in each star. And I think in figure 4.
Okay, I'm with you.
We show the abundances for all the elements that we could derive in the star up to the strontium, which is the light encaptured elements. So here we compared our study to benchmark studies published previously well-known studies like Carel.
Yes.
There's the giant stars from Carel and the dwarf stars from Cohen. And as we can see, within the error bars, our study compares well to the known abundances of the giants and dwarfs. Like they show the odd-even nucleosynthesis pattern for the light elements. The iron peak elements more or less tracks the iron content of the star, with the exception of chromium and manganese to an extent. And then the neutron capture elements show a non-enhanced distribution. That will come later, since here we have shown only till strontium, as most of the stars do not show an enhancement of encaptured elements.
Right. Okay.
So now that we have seen the trends of the abundances, we'll come back again, revisit the abundances a bit later. But let's for now go to figure 5 and see the distribution in the dynamics or the motion orbital parameters of these stars.
Oh yeah. Where are they? Yes. Figure 5, Toomre.
Yeah. So figure 5, this shows the Toomre diagram that has the azimuthal component of the velocity versus the v radial, the VR square, that is the v radial squared plus v along the z direction. So here we take the position of sun at the negative x-axis. So the motion of the halo, is clockwise, with a negative vz implying prograde motion and a positive vz implying retrograde motion.
Yes.
So some of the questions we wanted to address initially were the origin of lithium. So we wanted to see how lithium abundance varies as a most function of prograde versus retrograde, halo versus disk. So the blue line, the semicircle here, shows the loci of stars that are primarily having disk-like orbits.
Okay.
And the black dotted line demarcates the star from prograde to retrograde motion.
Gotcha.
So we see that lithium and the blue open circles are stars previously studied with known lithium abundances.
Okay.
And the blue circles are the ones we have newly added to the literature by this study. So blue ones are the new stars, green are the stars, all stars with lithium detection from literature. And we see that they actually do not show up difference.
Yeah.
Like stars are almost divided by half along prograde and retrograde. Like retrograde stars, it's a possibility that they are coming from other big events like Gaia Enceladus or other sub-dwarf galaxies. But in terms of lithium, as of now, we don't see any demarcation between the two. And even like disk-like stars show a similar abundances of lithium. And to bring to a notice, the red star that we show here, that is actually a star that shows higher abundance of neutron capture elements. So our process, that is enhanced primarily in our process. So again, like having a star with high abundance of our process and lithium together is a bit surprising, as our process is supposed to be formed by exotic events like neutron star mergers or collapsers. And to have the same amount of lithium in the star is a bit surprising, because that is supposed to like destroy the lithium, which is fragile.
Right.
And so it can tell us stories about the mixing of the ISM to bring down the lithium by this amount, and again enriching with our process winds. So this star is of particular interest, which we can take up. We are planning to take up later for a different study.
Okay. Well, we'll come back to that. Okay. Good.
Yeah. So.
All right.
In parameter space, like in orbital parameter space, they do not show any difference between prograde and retrograde motions.
Right.
Now coming to figure 6.
Two equations.
Yeah, we'll just come back to these.
Okay,
Yeah,
here we go.
So as a star ascends the giant branch, it is supposed to deplete its lithium as it comes in contact with the hot tenuous matter coming from inside via the convective channels.
Right.
So these convective channels end up destroying the lithium and bringing down the abundance of lithium by about 0.1 dex. So the black stars are the dwarf stars that are in the main sequence till the main sequence turn off, and the blue stars are the giants.
Okay.
That are on the red giant branch, or maybe the AGB. Very few of them might be in the AGB stage.
Yeah.
Okay. So we wanted to like model the destruction of lithium, that how the lithium goes down as we go up the giant branch.
Okay.
So if you go to the previous page, like the two relations, the scaling relations.
Yes, we had right here equations 1 and 2.
Yeah, so these are the equations like 1 and 2, like on the y, like abundances of lithium. So if we can inject a T effective, like an effective temperature for the particular star, we can end up with an abundances of lithium as it's depleting along the giant branch. So one is for the giant and one is for the dwarf.
Yes.
So applying these relations to the sample includes the stars from our study, as well as all stars previously studied for lithium. Shows that almost more than 85% of the stars fall within the 1 sigma distribution, 1 sigma of this distribution. Like the middle blue line is the empirical relation, and the black is for the dwarf stars, and the width shows the 1 sigma spread in the scaling relations. So as we can see, the majority of the stars do fall in this 1 sigma parameter space, and this empirical relation can be used for stars with lithium to determine the lithium abundances once we have the effective temperature. Or the stars for which we cannot detect lithium, this can tell us the expected lithium in a star commensurate with its evolutionary stage.
Yes.
Yeah. So, and the slope and sigma of the fit are also given like in the caption. And if we go to the next figure, we see the abundances of lithium as a function of metallicity.
Ooh, I like this plot.
This was as a function of effective temperature. The next is a function of metallicity.
Right.
So the Planck, like the 2.7, that is the prediction of lithium that one is supposed to have for the most metal poor stars in the early universe. So this is the first discrepancy we had in lithium. Like the most metal poor stars do not show that same enhanced level of lithium. And on the other hand, as the metallicity goes down, the slope tends to go lower. So the more metal poor stars, or in other terms, the oldest stars show the lithium abundance that is much lower than expected from the initial cosmological predictions.
Uh-huh.
And
Mm-hmm.
here we see the different stellar families like the EMP stars and the CMP stars, and the stars studied the very metal poor stars, and they all seem to fall along the same population for the giants and dwarfs, like it's spread all over. We do not see any clustering of any particular group of stars throughout the diagram.
Okay. Yes. Mm-hmm. Mm-hmm. Interesting. Very good. I like this plot. Mm-hmm.
Thank you. So if we go down.
Okay. Where are we at? 7, 8. Looks like we got as a function of other elements. Mm-hmm.
Exactly. So here we have found, like in this study, checking the abundances of the stars we found in this study, there are 2 stars that are actually a globular cluster escapees. So they show the anti-correlations, like sodium, oxygen, magnesium, aluminum anti-correlations, along with a decoupled CH versus CN bands.
Mm-hmm.
So some previous studies showed that there is a slight trend for lithium for these certain elements in globular clusters, which are not seen in halo stars. So here we have demarcated the globular clusters escapees in red, and the pink shows the CMP no star. And CMP no, that is carbon enhanced metal poor stars,
Right.
with no N capture axis in these stars, versus the other stars from the literature. So the black dots mark the dwarf stars again, and blue represent the giants.
Yep. Wow.
So here we see they again fall along this giant versus dwarf scenario. Like they really do not show any difference. So we have used sodium, which is a light element. We have used calcium, which is an alpha element. We have used chromium, which is an iron peak element. And we have used barium, which is an N captured element.
Okay.
So none of the elements do show any trend with lithium abundances, which is exactly what we expect.
Yeah.
But some previous studies by Aoki and Pasquini, they showed certain trends for lithium with these elements. So we wanted to check whether these trends exist in the currently known samples of lithium in globular clusters as well as the halo stars. But unfortunately, we failed to find any such correlations from the study.
Interesting. Okay.
Again, now if we come to the next figure, like we again probe lithium abundance as a function of distance from the galactic plane. So what happens to lithium as we go farther from the galactic plane? So lithium has shown a plateau as a function of metallicity. And as we go farther from the galactic plane, the probability of finding metal poor stars goes higher. So at the outer halo, we have more metal poor stars than we have in the inner halo and close to the galactic plane.
Okay.
So here we see a clustering, a clumping very close to the galactic plane. So the most lithium-rich stars are actually very close to the galactic plane. And as we go farther from the galactic plane, we can see a slight decrease in the slope.
Right.
So the abundance of lithium actually goes down as we go farther and farther away from the galactic plane. This can have some serious implications, like are they, if they're accreted from other dwarf galaxies, or if they're in the process of accretion in the Gaia Enceladus or the other outer halo regions, there should be certain populations with lithium-rich stars which you don't find.
Right.
So whether the lithium-rich component is primarily in situ, that is formed in the galaxy, or if they're migrated from other substructures, how do we not see the higher component of lithium in the outer halo or farther from the galactic plane, is the questions that we pose, that we try to find the answers.
It's a mystery.
Yeah, and the color code, like shown at the right, that shows the metallicity for the individual stars.
Wow.
Yeah,
okay.
so like then in this plot, we see mainly the function at the distance. Now, as we go down from figure 10.
Okay. Okay. Got some other abundances. Yes, very good.
Yeah, so here we show the abundances of light elements in stars that have lithium from the literature.
Yes.
in comparison to the new stars that we probe in this study.
Mm-hmm.
The red again shows, as usual, the star that is enhanced in N-capture elements. And as we can see, there is nothing like much I want to focus out of this figure, as all the stars seem to follow the well-known trends we see in the stars. For example, sodium, aluminium, magnesium, calcium. Like first two are the lighter elements, the next are the alpha elements. Magnesium and calcium, they show the typical 0.4 elevation that we see in case of halo stars.
Yes.
And similar for the titanium and silicon, they follow the general trends, and the same for figure 11. If we look at figure 11, that is for the heavier elements.
Oh, yeah. Mm-hmm. Scandium, chromium, magnesium, cobalt, nickel, zinc.
Yeah, figure 11, like scandium, chromium, manganese, cobalt, nickel, and zinc. They again follow the same pattern as we can expect under the paradigm of galactic chemical evolution.
Right. Okay.
And in figure 12, we show mainly the N-capture elements for the stars. Like I'd like to bring your focus into the two elements we could discover for the star as strontium and barium. So
Okay.
strontium is the lighter N-capture element, whereas barium is the heavier N-capture element.
Okay.
And with metallicities less than -2.4, we do not really expect S process to have a significant contribution. As the contribution from S process comes at a much later time, so metallicity has to be higher.
Okay.
So here we
process.
take like the strontium and barium. Like strontium, like the models of nucleosynthesis tell us that lighter N-capture elements, like the first peak of N-capture, like this yttrium, zirconium, and strontium, that peak can be contributed by core collapse supernovae, a certain type of core collapse supernovae with jets. But the heavier component, like the second peak and the third peak, they must be coming from neutron star mergers or similar like neutron star black hole mergers, or some exotic events that are very unlikely to be processed in supernovae winds. So,
right,
like the lighter element, we take the origin as supernovae, and heavier element, if we take the origin as, say, for example, say neutron star merger, like light R by heavier R, like LS, like lighter R process over heavier R process can tell us the contribution, the relative contribution from the two events.
Right.
So there's a third, in the panel at the bottom, we plot lighter R over heavier R as a function of Fe by H. And we can see they fall all along the 0.0 dotted line. So indicating that none of the pathways could be very dominating in case of the stars that we probe in this study.
Okay. All right.
So the red one, which showed an excess of, like the red one shows an European abundance of greater than 1, which is incommensurate with the R2 stars. Even for that star, we see the lighter over heavier to be 0.0.
Yeah.
None of the pathways are actually dominating in this, in the contribution of R process.
Yes.
Yeah. So, so finally in figure 13, and this is the figure where we probe the origin of lithium in the galaxy.
Back to kinematics.
So we figure in this figure, in the x-axis, we plot the angular momentum along z component. And on the y-axis, we plot the L perpendicular, that is square root of Lx square plus Ly square.
Yes.
So in this parameter space that is taken from DiMatteo 2019, we can differentiate the stars that are formed in C2. The stars formed in C2 are the bona fide members of the Milky Way from the kinematic point of view, whereas the region shown on the top is the population that is primarily populated by stars that are accreted in the velocity space. And whereas at the bottom, we show the mixed zone, which is actually the major component of this mixed zone is the Gaia Enceladus sausage or the Gaia sausage. So where did the most contribution comes in case of lithium? We can see that in the accreted zone, and the black dotted line demarcates prograde from retrograde as usual in the previous figure. In the accreted stars, and here the green open circles represent the stars with depleted lithium, like all are dwarf stars in this study, because we do not want to study the individual depletion of lithium in the stars, but in the dwarfs, stars that are lower than the speed plateau, we call them lithium poor. Stars that are higher than the speed plateau is 2.15. So stars higher than speed plateau, we call them lithium rich. So the green filled circles are the lithium rich, whereas green open circles are lithium poor.
All right.
So we can see in the accreted stars region, there is only one star that is lithium rich, and all the stars are actually lithium poor. So in the velocity space, the majority of the stars that are being accreted into the galaxy from other like the dwarf galaxies or streams or other mechanisms. So the amount of lithium-rich stars is very poor in the accreted systems.
Yes.
Whereas in case of the stars formed in situ, we can find again few lithium-rich stars. The majority would be lithium-poor stars.
Yes.
And even these stars here that are in the borderline, the ones lithium rich at the bottom, they are very close to the borderline. And in the mixed zone, that is the Gaia Enceladus region, this is where we can find significant contributions of both lithium rich and lithium poor.
Right.
But accreted, but this is a bit surprising as we expect the stars to show a similar lithium for like accreted, that we expect a certain number of stars to be enhanced with lithium even in accreted stars, which we do not really see.
Yeah, exactly.
Because studies of dwarf galaxies shown us that elevated lithium is there. Like elevated, I mean the speed plateau region is there, but which you do not see in the parameter space when you study the lithium stars in the galactic halo.
Okay.
And we also derive the orbits. Like we take the simple galactic potential, axisymmetric galactic potential, and using the Gala software, we produce the orbits of the stars backwards in time for stars formed in situ and stars formed that are accreted, which we show in figures 14 and thereafter. So in figure 14, we show a trajectory of a sample star that is so that is in situ, that is formed in the galaxy, and as you can see, the XY plane, they show a closed orbit.
Yes.
Like in the left panel, they show a closed orbit. Similarly, for XZ and YZ, they do not show, like they do not go out of bounds. The orbit do not go out of bounds. Whereas in case of accreted stars, we have shown only one, like an example of the stars in this diagram. But if you look at all the stars in the literature, we can see significant number of stars that are accreted do show open orbits.
Sure. I'll buy
So
that.
here in figure 15, we show the star for the accreted region. You can see it doesn't have exactly a closed orbit.
Yeah,
In
right.
YZ plane.
Right. Yep. Heavily perturbed. And then in figure 16, this is the mixed zones. Okay.
It is in the Gaia Enceladus region, in the mixed zone orbits.
Also open.
Yeah. They're also open.
Not closed. Yeah. Very cool. And how far back? So you took the current kinematics and so this is running the calculation backwards, right?
Yeah, backwards up to 5 gigayears.
5 gigayears. Okay. Very cool. Nice.
Yeah. So to conclude, like in this paper, like mainly probe the origin of lithium, like is the contribution towards the lithium abundance in stars coming mainly from the galaxy, or their accreted systems, or they are the Gaia Enceladus region. We also determine the complete abundances for several new stars that we find as a result of this study, like add the stars to the literature. They also quantify the depletion of lithium as it goes up the giant branch in terms of temperature, like the empirical relation governing the depletion of lithium with stellar evolution.
Cool. Very cool. Very, very cool.
And another thing also, like that was also surprising, like with distance from the galactic plane, the abundance of lithium is slightly going downwards.
Right. That's a mystery. Very cool.
Yeah.
Very nice. Very nice. Avrajit, thank you so much for walking us through this very lovely article.
Thank you.
It's great.
Thank you for the opportunity.
Sure. So you touched on it a little bit, and let me push on that a little bit. So we still have some mysteries here on lithium. And so where do you think we go, let's say, over the next 2 to 5 years? Are there additional observational campaigns underway to either nail down some more properties of these stars, or new metal poor stars that are out in the halo? Is there theoretical work that could be done? Is there laboratory astrophysics work that could be done? So just where do we go, let's say, over the next 2 to 5 years on the mysteries of lithium?
Yeah, like there are several things I would say one can do with the mysteries of lithium. One, like going right now, would be a precise non-LTE calculations of the lithium line. And along with the non-LTE calculations, the other thing that would be very important is a systematic global survey of lithium stars. Like all the stars adopted from literature will have systematics. Some use the color temperature, some use spectroscopic temperature, and there are different methods. And each method leads to a different stellar parameters, which in turn changes the lithium values. So a systematic study is like a systematic study for a large number of stars would be very essential to probe the abundances of lithium. One such study, I think, I'd point out to the R Process Alliance that is coming up with us maybe 2,000 new stars. Cool. So the stars of lithium with the R process rich stars having lithium elevated or depleted, that can have significant clues on the enrichment or the mixing of the ISM and trying to probe lithium toward the earliest epochs.
Nice. Very good. Well, I look forward to the next couple of years then on seeing seeing some of the mysteries of lithium salt. Detangled anyway.
Yeah.
Very cool.
That is the, I think, biggest challenge to us as astrophysicists, to disentangle the different processes that contribute towards this global picture of nucleosynthesis inside the stars and how we see them.
Right. And when does lithium get destroyed, and when and how, and all super duper. Or even if it's made in the right amounts in the Big Bang, right? Because that's another tension.
Exactly.
Right?
Yeah.
Between what Big Bang predictions say and what you observe. So lots of stuff on lithium. Very cool. Avrajit, thank you so much again for walking us through.
Thank you for having me.
All righty. That'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.